Good morning. Wow, this semester has really flown by, so it's time for the final exam, right? The final exam's coming up here pretty soon, in the next several days. So I did put together a practice set of problems. I went back and found a final from a previous year, and here's what the final looks like. So the final exam, as we've been talking about in class, instead of 4 problems, it's going to have 8. But when I look at the 8 problems, there are no A, B, C, D, E subsections. And it works. So sometimes students go, wow, twice as many problems. How are we going to do that in 2 hours? But it works. So historically, we have, averages on the final exam are comparable to the averages that we've had on the midterms. So again, it's a bit of a different format. 8 problems. Now, there's just no way to take 8 problems. There's no way to take 2 hours of work and sample everything that we've done in the course, 16 weeks, the entire semester. And so this really is just kind of sampling. I've gone through and tried to identify, I've broken everything down into 4 weeks at a time. There's kind of like 2 problems from the early part of the course, and then 2 problems from the next section, 2 and 2 from each of the 4 subsections of the course. Anyway, we'll take a look at the problems and see. It looks like I'm at the end of the problems. I need to go back to the beginning. Here's what that first page, the final looks like. So let's go ahead and get started. So here we go. The first problem says we're going to draw a rock drops. So I guess it's passive. The rock just dropped. It's intransitive. Intransitive? Yeah, intransitive maybe. The rock drops. It's not clear how that happened. From the top of the building, 60 meters high. How long will the rock be in the air? Now the assumption here is we're dropping from 60 meters from rest, so V naught is 0. It's Earth's gravitational field. That's another assumption, right? We're on planet Earth. And so the acceleration formula simplifies down to 1/2 g t squared. And so if I want to find out how much time this is going to take, what we can do is rearrange this formula and solve for t. So 2h divided by g, square root, that's 2 times 60 meters divided by 9.80 meters per second squared, square rooted. There's units of meters squared. There's units of meters top and bottom. Those cancel. Now there's units of seconds squared, but they're in the denominator of a denominator, which means they end up in the numerator. And so the units check out. I'm going to end up with units of seconds, and carrying out the calculations, I got 3.5 seconds. So it's only going to take 1, 2, 3.5 to drop 60 meters. That's a pretty good drop. Okay, and that's all the question asks. So what you find with these final exam problems is some of them are very straightforward as far as what you want to do. Others you're going to have to stop and think about, probably, more detail. Some of them may look complicated, but conceptually, when you think about it, there may be a relatively simple way to solve the problems, and some of them are just more complicated. Okay, so there's kind of a mixture. And if I feel like there is some, important topic that never got addressed on any of the midterms, I do, if that comes to mind when I'm writing up the final, I'll put a problem in that includes that. Okay, so that said, that's kind of I'm going to say that's a pretty easy problem, I hope. I hope that one doesn't cause a lot of difficulty, and so students are, your confidence is boosted a little bit by that. If the first problem is difficult, don't panic. either work that problem or move on to the next, either way, but make sure you come back and get a look at every problem at some point. Okay, second problem, we have a cable supporting a 2100 kilogram elevator. The cable has a maximum strength of 21,750 newtons, meaning if we exceed 21,750 newtons, this cable's going to snap. And so what is the maximum acceleration the elevator could undergo such that the cable doesn't break? Now, this doesn't sound like good engineering of elevators. I don't anyway, let's take a look and see. So here is a simple force diagram. So tension is upwards, mg is downwards, and we're going to allow for an acceleration upwards. So that says that the tension we're imagining needs to be bigger than mg if we're going to have an acceleration upwards to get the elevator started in the upwards direction. Now, the force of gravity, mg, comes in at 20,580 newtons. That already sounds dangerously close to breaking the cable on the elevator. Just holding the elevator in place sounds a little bit risky. I think we need a bigger safety factor. You know, back when we were in chapter 12 and we were talking about designing buildings and bridges and whatever, we said that typically there might be a safety factor of 3 or 5 or even 10 to make sure that whatever we're designing would never come near the limit of maximum strength. Anyway, this was a problem I ran across. So the largest acceleration we could come up with, T minus mg divided by m. So here is the largest tension, and remember, if we go any higher than that, the cable breaks. So this is tension minus mg over m. Ooh, look at that. We have to really be careful with this elevator, 0.557 meters per second squared. What about people getting on the elevator? Do we have to avoid that? Nobody can ride the elevator because the elevator itself already is too close to having the cable break. Anyway, what this problem is doing, this one was looking at some of the basic kinematics. This is looking at some of the basic force diagrams that we've worked with in the course. So identifying forces, so a lot of this problem is going to be based on what your diagram, it doesn't say you have to draw a diagram. Okay. I would draw a diagram, but anyway, you can take a look. These first couple of problems, I think, are pretty straightforward. Maybe they need to be harder. Let's see. So in problem 3, we're looking at a more detailed force diagram. In fact, this drum has mass. So the drum is 10 kilograms, the blocks are 12. It's connected with a string whose mass is really low. The pulley has a radius of 30 centimeters. It's a big pulley. It's like this big. The horizontal surface here is frictionless. What are the tensions in the two strings? This one sounds a little more involved. So, but it should be familiar if you go back and think of, chapters, chapters 4 and 5, and then chapter 10. So let's set up the diagrams. So that's the picture. Here is, I'm going to call this one M1. I'll call the one up sliding on the surface M2. Now remember, there's no friction here. So the force diagram is going to include gravity, it's going to include a normal force, and it will include tension 2. Now, the tension in this part of the string or the cable is not equal to the tension here. That pulley has mass, and we're going to have to exert a net torque on the pulley to get it to undergo a rotational acceleration. That's what we're going to need. So T1's got to be bigger than T2, and we have to treat them separately. So for object 1, I guess the object hanging off the side, the acceleration is in this direction. That says that the formula the laws of motion say that the acceleration then is given by m1g minus t1 divided by m1. So that first formula and the one below it, those apply to object number 1. Now if I look at object 2, this can't help but accelerate because there's only one force, T2, in the horizontal direction. It's unopposed, there's no friction. And so the acceleration here is just the force, T2, divided by m2. So you can see how all these forces are being identified here. And then, I didn't get all the forces on the pulley. Let's see. Oh, it doesn't ask us to. Okay. Anyway, so for the pulley, there would also be an mg and a normal force, but the mg and the normal force go right through the axis of rotation. They're not going to produce a torque. So the forces I'm interested in for the rotation of the disk would be T1 and T2. So here are the formulas for object 1. Acceleration is m1g minus the T1 over m1. That says T1 then can be expressed as m1g minus m1a. Now the acceleration of object 2, that's T2 divided by m2, and that says that tension on the side 2 is equal to m2 times a. Now I don't know the acceleration yet, so I can't calculate the tensions. But I have formulas that are headed towards creating the possibility of doing those calculations. So I'm going to have to include the pulley. The pulley's all part of this. If I look at a point along the edge of the pulley where the string or the cable is running, the acceleration tangentially along the edge is given by r times alpha. Now, the rotational acceleration is torque 1 minus torque 2 divided by the rotational inertia. The rotational inertia can be written as a shape factor times mr squared, and since it's a cylinder, the shape factor will be 1/2. So here are the masses of the blocks, here's the mass of the pulley, here is the shape factor of the pulley, and let's see where we're headed with this. So these are the torques. Now, torque 1 is due to tension 1 with a lever distance of r. Torque 2 is tension 2 times a lever distance of r. Now, what that gives me is a factor of r on top from the torques, as well as a factor of r on top from the linear rotational acceleration formula, and 2 factors of r below. And, you know, it's a miracle, but all the r's cancel. So it says that the results don't specifically depend on what the value of r is. Instead, they depend on what shape, how the mass is distributed, and the mass is distributed as a uniform cylinder. So that shape factor of 1/2 stays with us, but the r factors cancel out. Okay, interesting that it's the shape, it's the way the mass is distributed into whatever shape we're looking at. All right, so the formula then, object 1, I've got these 2 formulas. Object 2, I've got these 2 formulas. For the pulley, all of this rotational analysis leads to the acceleration is equal to T1 minus T2 divided by Cm. Now that one can also, why didn't I write that in terms of, oh, I wrote it over here. So I kind of skipped a step. What I should write here is, well, Cma, which I get from here, is equal to T1 minus T2. T1 is m1g minus m1a. That goes in here. And T2 is m2 times a. That goes right here. So this formula, I kind of did this column first, and then I moved to the left side. So we got all the way through the rotational stuff, and then I took the T2 and the T1 from here, plugged into this formula, brought the Cm over, And this is what I've got. So I've got shape factor, mass of the pulley times acceleration equals the gravitational force on object 1 minus m1 times the acceleration minus m2 times the acceleration. Well, I got three terms with acceleration in them. I'm going to have to bring those back over to the left side of the equation. So I'm going to bring all of that over to here. Now that leaves me with the acceleration times m1 plus m2 plus shape factor times the pulley. That should look familiar. I know it's been weeks ago. It's been a lot, many weeks back. And we did those 4 weeks on thermodynamics, right? So for better or worse, those 4 weeks of thermodynamics is kind of like, wow, does that mean we have to go back and remember the first 16 chapters? And you do. Okay, so this, I hope, is somewhat familiar. I'm solving for A now, and what we ended up with is the acceleration is a result of the gravitational force on object 1 divided by all of the inertias. M1, M2, and the pulley are all creating inertial effects, and it's going to reduce the acceleration. The only force actually driving this system is M1G, and that's right here. Okay, putting all the numbers in and the shape factor, the acceleration works out to be 4.055 meters per second squared. So this thing's going to accelerate, you know, at something like 4 meters per second squared. Now, acceleration was not what they asked for, if I remember right. What they asked for was the tensions in the string. So there's a region of the string that's under tension T2, there's a region of the string that's under tension T1. Once we've got the acceleration figured out, that was the missing piece, now we can go back and solve for T1 and T2. So going back to T1 and T2 and using these formulas, I'm getting tension in this region of the cable is at 68.9 newtons. The tension up in that upper part of the cable, 48.7 newtons. Now we knew, a couple things here check out. We knew that T1's got to be bigger than T2. And that is what happened. I guess that's a good sign. And then the gravitational force needs to be bigger than anybody. Gravitational force needs to be bigger than T1. And it is. I just wrote that down to compare. So I'm thinking there's a good chance we've got this right. Again, if you guys find discrepancies, I'm going to call them, if you guys find discrepancies in any of the notes that I've provided here, let me know, and I'll get those updated. Okay, so there's problem 3, and ooh, now it's starting to feel more like a final exam, right? Problem 3 was a bit challenging. All right, let's take a look at another example. Now, I think problem 4, we saw this in a somewhat different version, but pretty similar, back when we were preparing for midterm 3, maybe it was? Midterm 2, maybe midterm 2. Yeah, probably midterm 2. So these are from the first 6 chapters. I guess. These are from the next 5. Anyway, it's a momentum energy problem, and it's back to a projectile, 15 grams, I think some of the numbers are the same, running into a block, setting into motion, and then coming to a stop. And so the collision itself, the momentum coming in, equals the momentum after the collision. So energy is not conserved in the collision. That's an inelastic collision. I cannot use energy conservation to relate velocities and masses before to velocities and masses after, but I can use momentum conservation. Momentum doesn't go thermal. We don't have what we would call thermal momentum. Oh, the momentum's missing. Where is it gone? That doesn't happen. And so the momentum that we had in the projectile coming in will still be present after the collision. that says that the initial speed can be calculated m plus m over little m times v. Now, that's the collision. What about the slide afterwards? Because I'm going to need to calculate what v is after the collision. So once the collision has taken place, then we can use energy conservation. What we can say is that the kinetic energy still available after the collision is all going to go thermal as the block slides along the surface. So, and we said before that, you know, if you hit something with a projectile like this is supposed to be a bullet going really, really fast, the block's not going to be stable unless it's somehow, you know, constrained. Something is holding it onto a slot or something where it is going to go along the track. So something needs to be holding it in place, I would think. Anyway, the kinetic energy we have coming out of the collision has just occurred. This is the kinetic energy we have, 1/2 m plus m v squared. And that's all going to get converted into thermal energy, and we can calculate the thermal energy generated by friction by taking the frictional force and multiplying by the distance. That becomes the energy transfer due to friction. It's like work, right? So let's fill in some formulas here. The frictional force, there's my force diagram. The frictional force is going to be mu sub k times n, and n is going to be equal to little m plus big M times g. So mu sub k, m plus big M times g, all of that bundled together represents the kinetic friction force. So the m plus m's cancel. Those drop out, and it says that v squared is equal to 2, there's a factor of 2 here, mu sub k times g times d. So we can solve for speed v. Because we know the coefficient of kinetic friction, and because we know the distance that it slid, we can calculate that the speed right after the collision took place, right after the bullet hit the block, the block and bullet are moving at 6.82. Now the bullet's going to be moving much, much faster than this. Let's put the masses in. What was the mass on this? Oh, I'm sorry, I have drifted on to the next problem. So we need a barrier right here. Let's see, the velocity here is 6.82. That goes right into the formula we had derived over here, and that gives us 916 meters per second. Ooh, I almost crossed over into problem 5 inadvertently. So it's a good thing I stopped. So anyway, that's the speed of the projectile. And again, I'd have to go back and look, but I think it's many of the same numbers. It might be identical to the problem we did on a previous practice. I was trying to find new sets of problems, but this one matches up. Okay. All right, let's take a look at problem 5. So now we're moving into, this is like chapter 13. This is a ping pong ball that we're holding under the water. Now maybe you've done something like this, right? A ping pong ball or a beach ball, good luck holding that under the water, right? So what's happening now is the buoyant force for something like a ping pong ball or a beach ball, the buoyant force is much, much larger than the mass. So this thing doesn't just float, but it floats with most of its volume out of the water. If we hold it under the water, the buoyant force gets really, really large, and we would have to exert a force on it to make sure that it stays below the water. Now the numbers given here are that the ping pong ball has this little tiny mass of 2.40 grams, and it has a diameter of 3.8 centimeters. That sounds like a radius of 1.9 centimeters. So the mass is, we did get this right, 0.00240 kilograms. So make sure that when you convert into standard units, you move the decimal the right number of places. I think we did. Decimal got moved by 3. That's a factor of 1,000. The radius is 1.9 centimeters. Now, I went ahead and converted that into meters and then did the formula for the volume of a sphere, and I ended up with the volume of the ping pong ball in terms of cubic meters, 2.87 times 10 to the minus fifth cubic meters. So that's a tiny, tiny volume, but again, I've decided I want to work in terms of standard units. And the reason I want to work in terms of standard units is because I want to be able to calculate a buoyant force, and the buoyant forces are going to be in newtons, and newtons are going to require kilograms and meters. Now I could do it, it's a buoyancy problem, I could do the whole thing in terms of masses, but in any case, the buoyant force, here's my force diagram, buoyant force is upwards, mg is down, and the force that we're using to hold the ping pong ball under the water is also downwards. So the buoyant force that I calculated, it would be the density of the surrounding fluid, that's water. The volume of water displaced, that's the same as the volume of the ping pong ball, because it's now completely submerged, times g. So I put in the density of water is 1,000 kilograms per cubic meter. The volume of the displaced water, 2.87 from here, 10 to the minus 5, and then the gravitational field of Earth. And that says that the ping pong ball, once it's completely submerged, provides, well, it doesn't look like much. It's 0.2816 newtons. It's just a fraction of a newton. That doesn't sound like a lot of force. But the mass times gravitational field, the gravitational force, is much smaller. So the mass of the ping pong ball is much, much smaller than the buoyant force. In fact, it looks like the buoyant force is like 12 times as large. All right, so, so the buoyant force compared with mg is huge. We're going to have to offset, most of the buoyant force is going to have to be offset by us pushing down. Now the force we need is buoyancy minus mg, and that says 0.258 newtons. So it's not that this is going to be hard to hold under the water. It's just that once you let go, the ping pong ball accelerates upwards. And it's accelerating upwards because with F out of the way, B is 12 times bigger than mg. The net force is up, and the ping pong ball will accelerate upwards. Okay, there's going to be fluid resistance into this too. The water resistance will play a role, but the ping pong ball at this point needs to be held under the water with a force of 0.258 newtons. All right. Any questions on that problem? So that was problem 5. Too easy? Too difficult? What do you think? Now, I felt like, I think, looking back, I kind of felt like the practice midterms that we looked at were probably pitched at a pretty high level. I'm going to say this one, not sure yet. I haven't quite decided, but so far, problem 3, I mean, that was fairly challenging. Actually, problem 4 was too. Problem 5 is kind of conceptual. So if you understand how to calculate buoyant forces and how to set up a force diagram, shouldn't be too difficult. Certainly the math is not extremely difficult, but conceptually that, it takes a little thinking to figure out how the forces are related. All right, let's take a look at problem 6. Problem 6 is looking at a Doppler effect. And what it says is a person standing on the street, a police car goes by and the siren is on. And as the police car approaches, the person is hearing a pitch of 520 hertz. and then when the car passes, the pitch drops suddenly from 520 down to 480. Now this is Doppler shifted to a higher frequency, and this is Doppler shifted to a lower frequency, and they're not telling us what the frequency of the siren actually is. We could go in and solve that. Find out what the frequency is of the siren itself when it's not being Doppler shifted. Now the speed of sound, we're going to use our standard value of 343 meters per second. So that's, you know, a standard atmosphere at 20 Celsius. And then what else are we given? I think that's it. I think that's everything we've got. Okay, so here is the super Doppler formula. Now, for the approach, when the police car is approaching, the velocity of the object, or I'm sorry, the velocity of the observer is 0. The velocity of the observer in both cases is going to be 0. But the velocity of the source, which is the speed of the police car, is going to be subtracted in the denominator during the approach. That will give us a higher frequency, but it will be added once the car has passed. And that will give us the lower frequency. So you have to know how to use those plus and minus signs from the Doppler formulas that we have developed. All right, now we never really have to solve for the frequency of the source, so I chose to take these two formulas and divide them. So by dividing them, the frequency of the source drops out, and it says frequency 2 over frequency 1 equals V minus Vs over V plus Vs. And that's it. The Fs is canceled, the V's canceled. Now this is an approach. We've used this ratio approach or this division of formula approach, and it's a very useful algebraic technique for solving problems and canceling out factors that we aren't so interested in. So once we've done that, then I cross multiplied, and we have F2 times V plus Vs. That's the speed of the source. That's the speed of the police car, equals F1 times V minus Vs, where again, V is the speed of sound, Vs is the speed of the police car, and that's what we're solving for. So I want to be able to solve for Vs. So let's do that. Let's bring the Vs's to the left side. I've got a Vs times F2. Here I have a Vs times F1 with a minus sign. When I bring it to the other side, that becomes plus. Now what I'm left with are V times F1, and then V times F2. When I bring that to the other side, that becomes minus. So you've got to pay attention in the algebra, make sure that we're getting the plus and minus signs correct. But when I solve this for the speed of the police car, it's equal to the speed of sound times this ratio of frequencies. And putting all those numbers in, the difference between the two frequencies was 40. The sum of the two frequencies is 1,000 hertz. And what that gave us was a speed of the police car, 13.7 meters per second. So that's not all that fast, right? That's going to be like, what, 30, 35 miles an hour. It's not racing down the street. Maybe it's in traffic trying to find its way. So it's not going all that fast. But here's a way you could actually use frequencies, Doppler shifted frequencies, to determine the speed of something, right? All right. So again, 8 problems is not going to cover everything that we've looked at in the course. And let me point this out too. The final exam is worth 20% of the grade. That's not so different from a midterm. Midterms are a bit lower, but the final is not like the absolute determination of everything. I think from early in the course, I've tried to encourage everybody to make sure you're staying caught up. do well on the midterms. Don't let everything come down to a final exam, because the final exam is not an enormous portion of the course. It's a significant portion, but it's not like 40 or 50% of the grade, right? It's a smaller portion. Anyway, that said, let's move on. The last two problems we have are coming from the chapters on thermodynamics, and they have a very different feel, right? So those first 6 problems were coming from the mechanics portion of the course, and now we're moved into thermodynamics. Now the first part says, that's kind of an interesting problem. If we go into deep space, there's about 1 hydrogen atom per cubic centimeter. Now, does that sound like a lot of there's a lot of space out there. Does that sound like a lot of hydrogen atoms or not very many? So space isn't empty. It's pretty close to that, but it does have the occasional hydrogen and helium atom. Now, at 1 hydrogen atom per cubic centimeter, the temperature is at 2.7 kelvins. There is actually a temperature of outer space, and it has to do with the distribution of atomic energies, how fast are the atoms moving, and it also has to do with what's called the background of photons. So there's a residual background of photons left over from the very early phases of the universe, back when the universe was in more of a plasma state. The photons that were generated at that time, for the most part, are still around. And so we've got this background of photons left over from the early universe. So they want us to calculate the RMS speed and the pressure of the hydrogen. How much pressure would this number of hydrogen atoms create? Now, I don't know if you guys caught me on this, but notice that I asked 2 questions, and I didn't list them as A and B. Okay, I slipped 2 questions in there. Anyway, let's take a look. The VRMS still applies here, so I can put in 3 times R. Now, the temperature we're going to consider here is 2.7 kelvins. The molar mass, what should we use for molar mass here? Now, they tell us the molar mass for hydrogen 1. So hydrogen has different isotopes. There's not a lot of deuterium, hydrogen 2, in outer space, but there's an occasional deuterium atom. We're specifically asking about the VRMS for the simplest isotope. And the simplest isotope of hydrogen is a proton with an electron attached. It's not an H2 molecule, it's individual atoms. And so the molar mass, looking this up, is 1.007825. And I write that down because it turns out that almost all the isotopes of all the elements are very close to integer values, and you would say, it's easy to be accurate to better than 1%, but hydrogen is kind of the exception, and that's because a proton all by itself doesn't have any nuclear binding energy. When protons and neutrons connect to each other, the mass actually drops. The potential energies are actually negative. We'll see this in Physics 3B in the spring. I hope most of you, if not all of you, are around for the rest of the course during the spring. All right, then this is specifically for that individual proton attached to an electron. I wrote it all out with a lot of significant figures to see what it looks like. Now it rounds to 1.0, but it does not round to 1.00. It rounds to 1.01. So hydrogen 1 is kind of the exception. If I'm trying to be accurate to 1%, I can't use 1.00. I have to include this extra portion. So anyway, I made a big deal about that, but I'm going to include 1.0078. I'll include that many significant figures, kilograms per mole. Now I moved the decimal by 3 because I need this molar mass to be in kilograms. Remember, standard units throughout on this formula. So calculating the numbers, I got 258 meters per second. Really? Okay, now my first thought was I made a mistake. But my next thought was, well wait a minute. Even though the temperature is really, really low, the mass of hydrogen is also, the molar mass is exceptionally low. If we compare this hydrogen atom to, say, nitrogen or oxygen in our atmosphere, the nitrogen and oxygen in the atmosphere has like 30 times the molar mass. So that means they're going slower. And so it's both effects. The temperature that we are at in the room here is like 100 times that temperature, and since it's in kelvins, I get to say that. So if you're at a temperature of 2.7 Kelvin, that represents a certain amount of kinetic energy in the molecules, and if we want to put 100 times as much kinetic energy in the molecules, we would go to 100 times the temperature. If they're gas molecules, that's going to work really well. So going from 3 Kelvin to 300 Kelvin is a factor of 100. Now there's a square root there. That says in going from 3 Kelvin to 300, the VRMS is going to go up by a factor of 10. So at room temperatures, the hydrogen would be moving 10 times as fast. That would be like 2,580 meters per second. And that's what it would be moving at if we had individual atoms of hydrogen mixed in with our atmosphere. The hydrogen is so low in mass that it's going to go much faster than the nitrogen or oxygens. Okay, so the number works. And then it's kind of remarkable, you know, you're out in space. What does the VRMS depend on? Well, it still just depends on temperature. So the fact that there are very, very few atoms of hydrogen, that doesn't affect the temperature calculation. Temperature calculation is just going to come down to, or the VRMS calculation is going to come down to what temperature is it. So 258 meters per second. These atoms are really zipping around out there, even at this really low temperature. Okay, I don't want to say it, but that's kind of like part A, and this is part B. Okay, no, I didn't say that. There is no part A or B. Moving on to pressure. The pressure can now be calculated as nRT over V, but wait a minute. I don't really have moles. I just have individual atoms. So I'm going to go back and use Boltzmann's constant, little k, Boltzmann's constant, and say that there's one atom. So n equals 1, and then for the volume, I'll put in 1 cubic centimeter, which is 1/1,000,000th of a cubic meter. So, and then I'll put in the 2.7 kelvins, and let's see what we get. We get a pressure of 3.73 10 to the minus 17 pascals. So I was thinking here, how small could the pressure be? It certainly is going to be much, much less than a pascal, and it really is. 10 to the minus 17 pascals. A tiny, 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 really, really tiny fraction of just 1 pascal. Scientific notation, you really have to stop and think about it when you get a number like this. That is a tiny number. Okay. So anyway, that's conditions out in outer space. All right. Last problem on our practice final here. I was going to say, if you guys need to take a break, go ahead and take a pause, which of course, because I'm not going to take a break, and maybe you've already done that, or maybe you're realizing, oh, we're at problem 8 already, let's just see this thing through. So what we're going to do is take a 30-gram ice cube at 0 Celsius, and we're going to drop this into a container of liquid nitrogen at the boiling point of 77 kelvins. And then it's got some specific heat and latent heat information. But conceptually, let's just stop and think about what's going on here. So I've got a container of liquid nitrogen, and the temperature of that liquid nitrogen is 77 kelvins. So I've got liquid nitrogen at its vaporization point. That liquid nitrogen is right at the point where if we add any heat, it will start to vaporize. A little bit of heat is going to vaporize a little bit of that liquid nitrogen. So we really have to kind of reorient ourselves. Now, we're familiar with water, right? If I have a bunch of water at 100 Celsius, it's just getting ready to vaporize. What happens if I take water at 100 Celsius and I throw something in there, you know, a block of iron that's at, you know, 500 or 600 kelvins? Vaporization is going to happen, right? That's what's going to happen here. So from the liquid nitrogen's viewpoint, this block of ice coming in is really, really hot because the ice that's coming in is at a temperature of 273. So let's think about the process here. We're taking a little block of ice, 30 grams. It's starting at 273 kelvins, and I'm dropping it into this liquid nitrogen. That is going to release a lot of heat into the liquid nitrogen. So to find out how much heat is being released, that is MC delta T. It's 30 grams of ice. The specific heat for ice, we are told, is 2.10 joules per gram per Kelvin, and the temperature is going to drop 196 kelvins. So I hope this specific heat number remains constant over that enormous temperature drop. If it does, that predicts that the block of ice, which we think of as being cold, but in this problem the block of ice is really hot. That block of ice is going to release 12,350 joules of heat as it reaches thermal equilibrium with the surrounding liquid nitrogen. Now there's a lot of liquid nitrogen there, and so what will happen is a small portion of it will vaporize. How much will vaporize? Well, we're going to take all of this Q and we're going to use it to take liquid nitrogen at 77 Kelvin, and we just want to vaporize it. We just want to turn it into vapor at 77. We don't need to raise its temperature. We'll let the liquid nitrogen vaporize, and then it goes into the air, and with collisions with the other air molecules, it'll eventually warm up to the surrounding temperature. But that initial vapor coming off will still be at 77 kelvins. And that says we can use the latent heat formula, solve for M. So if I take 12,350 joules of heat and transfer it into the liquid nitrogen, I can divide that through by the latent heat of vaporization. Did I get this right? Oh yeah, that's the only one they gave to us. This is kind of too directed, huh? They kind of gave you just the numbers that you needed in this case. There need to be a bunch of spurious numbers in there. Anyway, let's say that the latent heat of vaporization is 200 joules per gram. So I scale it down to a gram, and that said that I will have 61.7 grams of liquid nitrogen vaporizing, leaving the system. Okay. So that's it. Interesting problem. So again, many of these problems, I'm going to claim, many of these problems are ones where you're going to have to stop and think conceptually, and then once the concepts make sense, the calculations aren't necessarily too difficult. And I'm saying that. I hope that's okay to say. So whatever questions you guys have, that final exam is coming up. Definitely stop by office hours. I've got office hours scheduled, and you can stop by and we can get the questions looked at. So good luck with your preparations for the final exam. I hope everything goes well with the final. Let me know what questions you have going into the final preparation.